When we study electricity, we often think of current as a total flow. But to understand conductors deeply, we must look at flow distribution. Imagine a highway. Total traffic is the current, but how many cars occupy each lane? That is what we call current density. Technically, current density, denoted as J, is the amount of electric current flowing per unit cross-sectional area of a conductor. To define it precisely, consider a small area element delta S on this surface, where current delta I is passing through it. If the current is distributed uniformly, the current density is simply the total current divided by the total area of the conductor. The formula is J equals I over A. It tells us how concentrated the electrical charge movement is at any given point. However, in real-world scenarios, current distribution might not be uniform. This leads us to the concept of average versus point density. The average current density is the total current delta I divided by delta S. It gives a macroscopic view of the flow. To find the density at a specific point, we take the limit as the area delta S approaches zero. This is the derivative form. The resulting equation is J equals dI by ds. This represents the point current density within the microscopic structure of the metal. Crucially, current density is not a scalar, it is a vector quantity. It has both magnitude and a specific direction of flow. The direction of vector J is the same as the direction of current flow, typically moving from positive to negative potential. Now let's consider what happens when the surface we are measuring is not perpendicular to the flow of the current. If the area element delta S is tilted at an angle theta, the effective area perpendicular to the flow is delta S cosine theta. In this case, the current delta I passing through the tilted surface is the product of J, delta S, and the cosine of theta. This relationship is perfectly described by the dot product of the current density vector J and the area vector delta S. Therefore, delta Y equals J dot delta S. This vector form is essential for solving complex electromagnetic problems. For an entire surface, we find the total current by integrating the current density over the entire area of the conductor. The final expression, I equals the integral of J dot ds, connects the microscopic current density to the macroscopic total current. Current density is more than just math. It is the bridge that allows us to understand how energy moves through our modern world. From microchips to massive power grids, the principles of J equals dI by ds ensure that our technology functions efficiently. In summary, remember that current density is a vector. It is area dependent, and it is the key to mastering electrodynamics. Keep exploring the physics of flow, and you will see the hidden patterns in every wire and every circuit around you. Understanding current density is your first step toward mastering the intricate dance of electrons in the physical world.